Okay, let's do a recap for a moment. What we saw before was that in quantum mechanics, if you have an information state represented by this ket over here, then you can always write this ket as a linear combination of so-called eigenkets. And an eigenket, this is the linear combination I'm writing right now, these are the eigenkets. The eigenkets have the special property that if you let an operator operate on them, it gives you back the exact same ket. So these eigenkets have this particular property. Here's an operator, you let it operate on this ket, it will just give you back the same ket, possibly with a number in front that we call alpha I, which is the eigenvalue. Now, why is this important to physics? It is important to physics because one of the postulates of quantum mechanics is that if you do a measurement on an eigenket, you are certain that the measurement will give back that number. The eigenvalue is not just any number, it's the number that you actually measure in your experiment. Now, if nature happens to be lucky enough to be in an eigenket situation, all information stated in an eigenket, you know with 100% certainty that measuring this thing on that eigenstate will always give you back that value. Now, of course, in general, kets are not eigenkets. Kets are usually these general kets, so you can write them as a linear combination. So you are not completely sure which of these values, these eigenvalues, will come out of your measurement. The only thing that you know, it's going to be one of the eigenvalues. And the probability of measuring a particular eigenvalue, as we saw before, is given by this coefficient modulo squared. If this is a big number, then measuring this observable on this general ket is very likely to yield the eigenvalue corresponding to this eigenket. If this is a small number, then measuring this on this observable on this general ket is very likely not to give the eigenvalue corresponding to that ket. So this is a probability that we see over there, and that's the connection between quantum mechanics in theory and quantum mechanics in experiment. Now, what I'm going to do now is going to make a statement about what if you do a lot of experiments. What we have here now is that this number will tell you if you do one single experiment, how big is the probability that will give back this particular eigenvalue. But what if you do 5 million measurements and you just are interested in the average? Now, each and every single one of the single experiments will give you back one of the eigenvalues. So 5 million of them will give you back a lot of different eigenvalues. You add all these together and you look at what the average is. What is that number going to be? Well, here's already the answer. The answer is given by the following expression. This here, what we're going to work out in a second, this here is called the expectation value or the average. Now, just to get all the confusion out of the way, let me immediately say that expectation value is a hideous misnomer. Expectation value sort of gives the impression that this is the value that is most likely to come out of your experiment, but that's not true. The eigenvalue that's most likely to come out of your experiment is the eigenvalue which has this as its biggest number. An average is something very different than the most expected value. This is just the average, but for some historical reason we call it the expectation value. It's an average. Okay, let's calculate what it is. It's not that difficult because we already know how each of the pieces can be written down. Here what we have is a bra. And we already know that a bra is just the bra here is nothing else than the ket complex conjugate, and we know how to write this ket. We can write this ket as a linear combination of these. So if you do that, you get a linear combination, but now with the complex conjugate of bras. So that's easy enough. Now this part, we don't even have to think about how to write that because we already know that. That's this linear combination right there. Now of course, it's a linear combination, but let's not write it with the summation over I because we're already using it for the bra over here. Let's use the J so as not to get these two summations mixed up. But that's easy enough. That's really just this expression. And then there should be this A in between, but we know of every piece how to write it, so let's connect it all together. Here's that one, which we can write as this. It will give you one summation AI star with the bra. Then there's the A, put it over here. And then there's this part, the ket can be written as this linear combination. There you go. There we are. So that's that. Let's clean up a little bit. The summations can both be put on front. Here's a number, there's a number. Numbers can be put in front as well. So just to clean up a little bit, let's put all the summations in front and all the numerical values in front as well. So this is what you get. There you go. Now, moving on from this point, what we have here now is this other bracket, but now the A is operating on an eigenket. Here it was operating on a general ket, now it's operating on an eigenket. And for an eigenket, we know exactly what the outcome is. This part really is just the eigenvalue times the ket itself. That's just this expression right here. So this part is easy. So by using that, we have now replaced the operator by an eigenvalue, and because it's just a numerical values can be put in front of everything. So we've cleaned up a little bit more now. And we have this expression right there. Now this can be cleaned up even more, because what we have here now is a bracket without an operator in between, just a bracket of this ket and this bra. And we've seen as one of our postulates that they can be orthogonalized, as it's officially called. By this I mean that if the bra and the ket have the same index, it's the same bra and it's the same ket, I equals j, then the outcome of this bracket is going to be 1. If they're not the same, it's going to be 0. So in other words, we have a summation here of all kinds of psi i's and psi j's, but all of them are going to be 0, except for that one when I is equal to j. So that means that the summation over I will only give back a non-zero value at the moment that I is equal to j. So we can just replace the summation over I by this expression where every I has now turned into a j. So really what this thing does is just cancel out one of these summations, and ultimately what we have here now is now a bracket of j and j, which of course is unity, so we can just move it all together, and we end up with this expression right here. Now, what does the expression look like if you clean it up even more? Well, there's this number here, complex conjugate times the number itself, which of course modulo squared alpha j. So that's the final expression. So after a number of steps, we started out with this bracket here. So a number of steps, we got this. And before, I promised you that this is going to be an average value, that by stupid historical reasons called a expectation value. It's an average value. Now, how can you tell that it's an average value? Well, the answer is just by reading what it says. In any branch of physics where you have probabilities, an average you calculate by taking the probability of measuring a certain number times that number itself and then adding it all up together. This is how you average things. Take the probability of a particular, of finding one particular value, multiply it by that value, and add all these numbers, and you get the average. And that's what I'm doing right here, because here's aj modulo squared, and we already saw before that that is exactly the probability that a measurement will give back this eigenvalue. So what we have here is probability times measured value, add it all together, it's an average. This expression is an average. Which is good, because we now have two ways of connecting theory to experiment. This one says something about the probability of measuring, in one single measurement, measuring the eigenvalue alpha I. And this one tells you something about what if you do 5 million measurements and you take an average. So we now have a way to connect our quantum mechanical theory to averages and to single measurements. And that's a very big step forward. All right.